So to finish up our hypothesis test, what we'll need to get to is the p-value. The value for the p-value, which is our probability of seeing our sample statistic, that'll lead us down the path of, are we going to reject the null hypothesis or fail to reject the null hypothesis? And with that, we can get a structure for how we'll write our final conclusion. So before calculating the p-value, we need to keep in mind what type of test are we doing. So we know that we're calculating the probability of seeing our sample statistic or more extreme correctly. So, one little piece I want to add here, the p-value will represent the probability of seeing our sample statistic or more extreme under the assumption that the null hypothesis is true. So under that null hypothesis, that's very important that we're building it all around the assumption, and then we want to see how extreme is our sample statistic. So again, with the right-tailed test, to find our p-value, so we'd build our sampling distribution all around that proportion from our null hypothesis, and then our sample statistic should land somewhere on the right-hand side. And so to find p-value, you're going to find this area in the right tail. So p-value as a probability will be the area under the curve to the right-hand side. For the left tail test, it'll be the same idea, so built around that proportion from the null hypothesis. We'll have some sample statistic landing on the left-hand side. And with this, we'll take the area to the left, and that area under the curve will be our p-value. So again, we want to see if that probability is low, or is it small or not small. And then with the two-tailed test, built around our null hypothesis, and then this is where your sample proportion might land on the left-hand side or the right-hand side, but whichever side it lands on, you're going to double that tail area. So whether it's the left tail or the right tail, you combine those two. So with that one, to find p-value, you're going to take 2 times whatever the tail area is. So once we find that p-value, there's 2 possibilities. We're either going to reject the null hypothesis or fail to reject the null hypothesis. Those would be our 2 main conclusions. It comes down to whether or not the p-value is small or not small enough. But if the p-value is small, so that links to our sample is unlikely. So our sample was unlikely under that null hypothesis. So it is statistically significant. So if we see something rare occurring, it's statistically significant, which means we get to reject that null hypothesis. And then for wording our conclusion, what we want to talk about is that we have found evidence for the alternative hypothesis. That's our big claim at the end. If we fail to reject the null hypothesis, so that's where our p-value is not sufficiently small, so we're seeing something with a high enough probability that it could have just happened randomly. The idea being our sample could have occurred just by random variation. So it could occur due to random variation. So it is not statistically significant. Basically, nothing significant occurred. You saw a random sample, and it fairly lined up with our null hypothesis under that assumption. So in this case, what would happen is we would fail to reject the null hypothesis. Again, this is different from, we're never proving the null hypothesis. You can either reject the null, or we just can't get rid of it because our evidence isn't strong enough. So we would fail to reject the null. So in our conclusion, because it's all about whether or not we have evidence for the alternative, and in this case it's that we don't have enough evidence. The evidence isn't strong enough for the alternative. So with this, what we need to think about is, well, what's considered small? At this point, it could be kind of based on opinion of what you think is a small probability versus a not small probability. So what we need is an actual cutoff value, and that's where significance level comes in. Sorry about that. Significance level. So significance level is given by the symbol alpha, and that'll be our cutoff for what's considered small or not small. So typically alpha is 0.05, this 5% significance level. That's what we assume most of the time. There can be other values, like here I listed 0.1, which would be 10% significance, or 0.01 for 1% significance. Sometimes they'll adjust those based on what they're doing and how significant they want the results. But typically what you can do is assume we're using the 0.05, assume alpha is 0.05, or you can think of this as 5% significance, unless told otherwise. So in the problems, they might not specifically state what the significance level is, and you'll just use 0.05. We'll be using alpha of 0.05 probably like 99% of the time in this class. It's the most common form, kind of like with confidence intervals, and we'll talk about connecting confidence intervals, how 95% is kind of the most common one. It's the most commonly used. It's just kind of a nice balance between like really high significance or lower significance. Similar idea with alpha equals 0.05, and we'll talk about how that significance and confidence levels relate. So what this does is it gives us a cutoff of area for what's considered small or not small. So what we could think of is, say we're running a right tail test with a significance level of 0.05. So we build our sampling distribution all around our null hypothesis. What this significance level does is it creates this cutoff. What it's doing is it's cutting off an area of 5% of our data. So it cuts it off, so we have this area of 5%. And then when we go to find p-value, so say I land out here in what I just highlighted, say I had a sample statistic land out there or out there. When we're landing to the right of that cutoff, we're creating areas for our p-value that are smaller than 0.05. That area wherever we cut off would be smaller. So over here is where we're seeing very small p-values. So what we say is anything that lands to the right there, that's where we would reject the null hypothesis, and specifically coming through with p-values smaller than 0.05. Whereas if we land to the left of that cutoff, say I'm just over here, and then I went to find p-value, which would be area to the right, we'd have a large area, or it's not necessarily large, but it's larger than 0.05, and that's not considered small. So if we land to the left-hand side, then we would fail to reject the null hypothesis. So what this does is it creates kind of a rejection region for where would we reject the null and that our p-value is small, or where would we fail to reject the null and say the p-value is not small. Something to think about is if we have our sample statistic and say I'm landing about here, that creates kind of a decent area. Maybe that would be fairly close to 5%, but still smaller. Then imagine as I go further and further out into the tail, and say I was way out here, we get to this point where we could even create areas of basically 0, and that would be very, very significant in that it would be getting a sample statistic that's nearly impossible under that null hypothesis. So we'd be finding very strong evidence for the alternative hypothesis way out here. Whereas if I'm close by that cutoff where I'm like almost nearly at 5%, that's not as significant. I would still reject the null hypothesis. I would still have evidence for the alternative. and it's just okay. So something that happens with p-value is the further we go out into the tail, the more significant that evidence is. So a phrase you might see come up is the smaller the p-value, which would relate to the further we are out into the tail. So the smaller the p-value, the stronger the evidence is for the alternative. So the further we get out into that tail and the smaller the p-value gets, the stronger the evidence is for that alternative. So to kind of tie it back to the coin flipping example with that 75% sample statistic that we found, we had this very low probability, and it's because getting that sample statistic was nearly impossible. Whereas maybe if I flipped the coin 50 times and saw 60% heads, maybe that would still be significant. It's just not as strong of evidence. It's a little closer to happening just by random variation, and we're getting closer to that cutoff of where we failed to reject versus reject. But the further we get out into the tail, the stronger that rejection is of that null hypothesis. So let's see how we evaluate our p-value. What I'm going to do here is kind of skip a lot of the steps of the hypothesis test and just jump to p-value. And once we have that probability, how do we evaluate it? And then how do we write our sentence conclusion? So where we end up with these two possibilities, like when we reject the null hypothesis, that's coming from if we take our p-value and we're going to compare it to our significance level. This is where our p-value is small, so it would be less than that significance level. And then failing to reject the null hypothesis will come from when we look at that p-value and compare it to the significance level, which is typically going to be 0.05 nearly almost every time. And that's when the p-value is not small, so when it's larger than or equal to that significance level, then we would fail to reject the null. Okay, so we're going to see some similar examples as well as a kind of new one. So the emission standards, so just as a reminder of our null and alternative hypotheses here, what we'll have for our null hypothesis is assuming the proportion is 0.8 and we're trying to prove that it is smaller than 0.8. So then from there we would go through, check the conditions, set up our sampling distribution, and then finding p-value would go about calculating the probability in GeoGebra. What we're going to use here is the fact they're just giving us p-value. So let's just skip to the evaluation stage of this. So our p-value is 0.0009. Very small p-value. But what we want to do here is kind of prove that it's small enough. So what we're going to do is basically set up for the evaluation that I wrote up here as if we have alpha next to it, what symbol would go in between, the less than symbol or the more than or equal to symbol. So what I'm going to do is go ahead and write 0.05 next to it. And then we just need to evaluate, is the p-value small or larger? And in this case, our p-value is smaller. Something that can help here, since evaluating decimals can sometimes be tricky, especially when the numbers are closer to each other, I found it can help students to change these to percentages. Like this would be the equivalent of 0.09%, and this would be 5%. And sometimes that's just a little easier to see which is smaller. So if it helps, you can do that extra step. So what we get from this is the p-value is small. So we are going to reject that null hypothesis, which means we have evidence for the alternative. In terms of other resources, what you'll see them do is just do this comparison and reject the null hypothesis, but I find writing these extra pieces can really help. Is the p-value small or not small? Are we rejecting the null or failing to reject? Do we have evidence or not have evidence for the alternative? So when we get to our sentence, what we're going to do is include what we're doing with the null hypothesis. So we are going to reject the null hypothesis. Then what we need to do is state what's the p-value that we found. So I'm going to go with a p-value of 0.0009. And then my statement can be that there is evidence for this alternative hypothesis. So essentially what we did is we were able to go, not that, yes this. So we're able to prove that this proportion is less than 0.8. And what you can do here is, for wording for the alternative, just kind of look near that word test, and then you'll have some kind of information to draw from in making your sentence. So I'm just going to say there is evidence. And then I'm just going to kind of copy less than that, less than 80% of their fleet meets emission standards. All right, so that's what we do with the p-value, is grab the value. Typically we'll be finding that from GeoGebra. We're just kind of skipping a step here, but take the p-value, compare it to our significance level, and just figure out what symbol goes in between. And once you figure out what symbol goes in between, these three pieces come through: whether or not the p-value is small, fail to reject or reject, and then whether or not we have evidence. And once you know whether or not you have evidence, that'll set up your sentence structure here. All right, let's look at this next one. So looking at poverty rate, which we did before, and we're trying to prove that it is different. And what we're going to use is they found a p-value of 0.273. And what we're going to do is compare that to our 5% significance level. Again, notice here, sorry I didn't emphasize this with the previous one, but they didn't state the significance level, so we're just using 0.05. How this will change is if they added wording in the sentence of like use a significance level of 1%, like there'd be extra information to change that value. But because they aren't stating anything, we're using 0.05. Again, it might help to change these two percentages. So like this p-value is a 27.3%, and our significance level is always 5%. So with that, it might be clear that that p-value is definitely larger. So here we would have the p-value is not small, which means we failed to reject the null hypothesis. So this null hypothesis of 0.148, now again, we didn't prove that it is 14.8%. We just don't have enough evidence to say it's significantly different from 0.148. So this is where there is not enough evidence for the alternative. So the wording for my conclusion here, I would go, we failed to reject the null hypothesis. And then I'm going to state the p-value. So stating my evidence, or rather lack thereof, with a p-value of 0.273. And then what I want to do is the sentence should always be phrased in terms of the alternative. So up above here in part A was that we had evidence for the alternative. And now I'm going to write in a way that portrays that there's not enough evidence for the alternative, which again, in the wording, you can look for the kind of structure for how you want to phrase the alternative. So we wanted to test, and sorry, this says country, but it should be county, if their county has a different poverty rate than the rest of the US, and we didn't have enough evidence to prove that. So we could say there is not enough evidence their county has a different poverty rate, or you could even say significantly different poverty rate than the rest of the US. So in terms of sentence structure, the difference between rejecting the null hypothesis and failing to reject is really this difference of saying there is evidence for the alternative versus there's not enough evidence for the alternative. So with these structures, they'll be very similar. We just have to be sure, are we stating we found evidence or we didn't find evidence? All right, this last one's a little different, but I wanted to show you an example with this where here they're not really dealing with any proportions. So drugs that prevent seizures sometimes have unwanted side effects such as depression. A researcher wants to study such a drug and look for evidence that such side effects exist. So that wording right there is setting up our alternative hypothesis. They want to find evidence that there are side effects. So what we can do here is just write a null and alternative hypothesis in words. So what we would assume is that there aren't any side effects, and we want to find evidence that there are side effects. So with this, they gave us a p-value of 0.06, which would be the equivalent of a p-value of 6%. So we're going to compare that to our 0.05 or our 5%. Which means our p-value is bigger. We have a large p-value here. So the p-value is not small. So we failed to reject the null hypothesis, which means there's not enough evidence for the alternative. So with this, I would write failed to reject the null. So basically, I can't throw out this idea that there are no side effects. Even if there are some side effects showing up, it's not significant enough to completely say there aren't. It could have just happened by random variation, things like that. So I would say with a p-value of 0.06, there is not enough evidence to conclude that such side effects exist. All right, so little piece missing from our process at this point is getting into GeoGebra and calculating, but we'll look at in the next video kind of all these steps together, putting it all together and running through full hypothesis tests. But this is how the hypothesis tests are going to wrap up once we get that p-value from GeoGebra, getting that number, comparing it to our significance level, and then writing a sentence conclusion about whether or not we have evidence for that alternative hypothesis.